So actually, just a bit of pretext. I gave this talk in 2017. Like 2017, Niall Smith in Cork IT ran the International Space University Summer Program in Cork IT, which is, comes from the very prestigious program for trainee astronauts and all that. So, like doing an MBA over the summer for astronauts, they pay a fortune for it. And I was involved. I'm still doing a PhD after all these years, getting near the end under Niall. So of course he wrote me in to do a whole ton of admin stuff, and so 2017 through February, March, April, May was just absolutely crazy. The opening night of that was late June. I remember on the night of the opening of the International Space University thinking, I'm off the hook. Thank God I can relax. I'd also taken other modules in college. A colleague that retired at no notice, and I literally couldn't think. It was that brain dead by late June. And as we were literally having wine and cheese and the opening night, Niall puts his hand on my shoulder and says, Kev, you're giving a talk to astronauts on August the 4th about big data and astronomy. And I just thought, oh dear God, no. What's big data? So the thing was that actually that's where this talk spawned from. And I had to spend the whole of July with my head stuck in books learning about AI and learning about big data and astronomy. And so that's kind of where the talk came from. I kind of rejuvenated a few years ago when we were talking about, would we give a talk? I thought maybe it's time to reinvent it. What with the advent of AI and all the rest of it. But actually, what's been really interesting is that actually in terms of astronomy and how we're doing astronomy and big data, actually, I suppose in a sense, thankfully, but maybe, we'll have more to say in that in the future, it hasn't been permeated or influenced by these large language models. AI and big data astronomy is still it's such a gargantuan approach to a new way of doing astronomy that it's still, I suppose, where it was in 2017. But that's no mean feat. So the thing is that I suppose what we want to just start off with is, as I say, for those who've seen my talks before, the first 6-7 slides are probably quite similar. I start off a lot of talks quite similarly. But the thing is that what we want to kind of consider about astronomy is that we are actually trying to tackle the hardest questions there are, I suppose, in relation to nature. Some of the hardest questions, maybe biologists have something to say about that. We're tackling questions about the origin, nature, and fate of the universe, and indeed the origin and fate of nature of Earth and of life. But the thing about astronomy that's different to other sciences is that it is and has always been what we call, this is a very, talk with trendy term, disruptive. Every time we have a revolution in astronomy, it's because we've invented some sort of piece of technology that allows us to look at the universe in a completely different way. And in doing that, we kind of, I suppose, in a sense, I won't say get smug, but we can go along kind of thinking, oh, we've got a handle on things. And then we build on that and we develop on that until something else disruptive comes along and makes you realize, right, okay, we've got to start from scratch all over again. And that's, I suppose, what's been the same for many, many different generations. The jump from Tycho Brahe to Galileo using the telescope, well, actually, it took decades for the telescope to really get going, but nevertheless, was very, very disruptive. Suddenly, we could see the planets as disks, that type of thing. Then, of course, the invention of the spectrometer, or spectroscope. Whoop, I've not to touch that screen yet. Can we drop that down?
It'll drop down again.
Yeah. For those who don't know about spectroscopy, basically what we can do is, by analyzing the light being emitted by a material, say when you combust it, you can infer the chemical structure of the material. So once we could look at the light from stars through spectroscopes, we can analyze what is their composition. Again, disruptive. And then, of course, in the 20th century, by realizing we don't just have to look at light, but many different parts of the electromagnetic spectrum, we can infer entirely new different ways of understanding nature itself by ways we can't see it directly, for example, through radio telescopes. And we've been massively successful at that up until quite recently. We have basically pushed and we are pushing and will continue to push individual instruments and individual capabilities to their limit. The European Southern Observatory, of which Ireland is a member now, is part of that. Not only with the amazing optical telescopes, but also with the millimeter telescopes, the ALMA array. And then in space, these are sort of slides you may have seen before if we give talks of that. Nothing short of armadas of space telescopes, Space Hubble, Webb, what have we got here? Herschel, WISE, Kepler, and Switzer. I don't remember all the space telescopes. But all of these telescopes giving us profoundly new and intriguing views on the universe. We'll take a look at some of those results in a few minutes. Likewise, around the solar system, space probes to the outer solar system and beyond. And of course, my favorite, an absolute revolution of analyzing Mars from the orbit, as I say, from the orbital to the microscopic or the molecular level through a phased program from the late mid-90s, orbital reconnaissance, geochemical landers, exobiological landers, supposedly Mars sample return, and then humans there for science reasons. And the results have been spectacular. You can see sedimentary layering on Mars. We know it was habitable. It's actually a planet that's still defined by vast amounts of water there. The gravimetric analysis of Jupiter has given us insight into how the planet itself is structured on its inside. We've been out to Pluto, an enigmatic world with plenty of activity and even, or I suppose, an exosphere, if not an atmosphere. But the thing is that the sum total of what we've done in analyzing the solar system is pointing to something different than just a group of worlds. It's pointing to a dynamic system with the Oort cloud, the Kuiper belt, a system of trillions of worlds, a system that's still evolving, a system that has a dynamism to it, a system actually with some anomalous readings in the outer solar system we still can't figure out yet, and a system that, I suppose, more than anything else, we realize we're only beginning to get a handle on. It's not 8 or 9 planets, irrelevant debate in a way. It's trillions of worlds in a dynamism that's continuing and that interacts with the rest of the galaxy, and that shapes how Earth actually unfolds, and that will shape how Earth unfolds into the future. When we go further afield, we see similar. In fact, this is one of the best artist impressions of the galaxy that we have. It's a barred spiral galaxy. We're somewhere out here in the Orion spur between 2 spiral arms. But it's an artist impression, actually based on observation of just hundreds of stars. We now know that billions of course, but just hundreds of stars is what we used to build that image. But just getting back to and nudging towards the big data idea here. This is a Spitzer image. Spitzer was a small infrared space telescope before James Webb. About a 1 meter mirror. I can't remember, it was 1.6 meter mirror. Nowhere near the resolution of Hubble or James Webb, but this is 50,000 images from Spitzer knitted together. It's 1/16 of the length of the Milky Way galaxy, and it shows everything that's green is organic carbon in interstellar space. We now know that over 90% of interstellar space is made of the carbon in space is organic carbon. We got the Eagle Nebula up here somewhere. So, what we can do when we point towards a kind of, I suppose, a bigger sphere of view. The famous Hubble Deep Field, what's this going back to now? 31 years or something like that, of which we've produced many of these. But this one image, it's the most analyzed image in astronomy. There's, I think, something like 4,000 papers. It's thousands of papers just analyzed on it. I remember the day I remember just kind of thinking, I don't recognize this. And I've been into astronomy for decades. There's something strange going on here. And the thing is that it's, of course, about 11 billion light years away. Every point in it, bar 1 or 2, is a galaxy, not long after the universe formed. And we now know that if Hubble imaged the entire sky, it would see this everywhere. It took several random images. But again, and this points to where the big data idea will lead to in a few minutes. And it's a statistic I love giving, is that if Hubble were to image the entire sky at this resolution, it would take it 900,000 years to do it. That's unbelievable. Now, as we'll see with LSST, the Vera Rubin telescope, it nearly does this every 3 days. That's where we're going. So the thing is, and then of course, direct evidence that we are in a gravitationally dominant universe, that general relativity dominates, and we'll talk a little bit more about that as well. Then when it comes to looking for planets around other stars, of course, there's been a revolution here. This is the SPHERE instrument in the European Southern Observatory, detecting hundreds of protoplanetary disks. The ALMA array for seeing what we think are carved out rings from where planets are forming right now. And of course, the Kepler Space Telescope detecting thousands, actually, isn't it? We're up near 6,000 planets verified, and even systems where we think there are Earth-like planets, if not Earth-sized planets. Proxima b, art of impression, next door neighbor, we believe, maybe an Earth-like, or could potentially an Earth-like planet. And it's not just that we are actually making amazing strides forwards in all these different ways. What we're also doing is taking leaps of perception, that we can look at the universe and with new eyes increasingly. So to kind of finish off this whistle-stop tour of where we've come to, and what points to a big data, big survey way of approaching astronomy is, I decided to choose this image here. I use this in my James Webb talk, so if any of you have seen that, you might have seen this. It's the Carina Nebula. It's about 7,000 light years away. It's one of the biggest star-forming regions in the Milky Way. It's hundreds of light years across, with thousands of stars being born. And this is a really good ground-based image. Now, I have to just have a caveat here. This is a really good ground-based image before image stacking. So I'm going to do ground-based images a little bit of injustice here as we move forward. But just to show the difference, again, in perception when we build better instruments. So I'm going to target and focus in on this kind of little rectangular region here. So this took a lot of time to align these. So there we go. There's this rectangular region here, just kind of focused in on the same image. Oops. And here's Hubble's image of it. So there's the difference. Oops, I'll go for it. Okay, sorry. So I'll keep going back and forward a bit. So you just see detail that we just, so I don't know whether you can see it here, but we've got Mystic Mountain here, you know, where we've got the star forming, and Eta Carina here, which two massive stars, and there are zoomed images. By the way, this is in my web talk, this is a 29,000 pixel wide image. We can keep zooming in and zooming in and zooming in, and you just don't see pixelation. 29,000 pixels across. But if I just, even at this resolution here, Earth-based, ground-based, above the atmosphere, just pick some point in it, and just you realize that with this image here, there's only so far you can go. You do need this image to see the greater detail, whether we pick one of these pillars here or, as I say, some cloud formation. And then, of course, Webb came along. So let's focus on what it could do. So one of the first images it released was called the cosmic cliffs. And in fact, it's part of the Eta Carina. It's right here. This little dip, oh, sorry, I've done it again. This little dip right here. And so let's align that. So zoomed in a bit more. So here's the cosmic cliffs right here. And then here it is. It's the same image, just blown up, but you can see what I'm going to do. I'm going to plant Webb on it now in a minute. Now, as I say, I'm doing this a bit of injustice because I think with image stacking these days, we would get a really crisp image from the ground. So I'm being a bit unfair here. But this is the best we could do, say, 10 years ago. Here's Hubble's image of that. There's the difference. And here's Webb. So we see how we transcend from one perception into another. And I'm going to step out of the PowerPoint and go into the full-scale image in this. Can get my glasses on. Where is it? Bring it up again. A couple of this. I didn't want to bring the video actually. Previous no more. Sorry. There. Well, if you were. Bear with me a moment. Oh, it's got it there already. Brilliant. With File Viewer, actually, preview and they've done on a Mac doesn't actually. You get lossy. It doesn't show an image and zoom in properly. So if I zoom in on this, we just don't see pixelation. We're just getting ever confined detail, and we're at the tens of billions of kilometer detail here, by the way. So if Webb returns this in a few years, you will see movement. In fact, that you have two pictures of the pillars of creation. It took about 3 days to align them, and you can actually see movement all over the pillars of creation from 25 years apart. Wow. It hasn't been published actually, and I think I need to get it up somewhere. But however, and this is, I say, is what happens when you just keep improving things. Then when you start to apply computer algorithms to try and observe the Doppler changes or the movement in this is now the latest that we can see from the pillars of creation. So just think back to the Eta Carina image. And now we're actually inferring three-dimensional movement and structure within the cloud. This is what a better instrument allows you to do. Not one great on the screen, actually, just with the zoom, but I think it's giving the impression, isn't it? You can see three-dimensional structure. There's a new solar system forming right there, a new star. Anywhere, there's another one right there. Anywhere you can begin to see the ejection clouds from the actual. So what happens is when you see these cones, it's a collapse of angular momentum, actually, and then along the star's poles, it ejects matter as things start to collapse. So the pole of this star is probably pointing in this direction. Amazing, isn't it? So the thing is that this is where we're at in terms of, I'll just pause there, the best single instruments that we can do. I'll get my PowerPoint back somewhere. Yeah, sorry. I want to do one other thing as well. I don't know how well this will happen over Zoom. So with better instruments, we also, as I say, traverse different, I suppose, levels of perception, levels of understanding of the reality of what it is we're trying to analyze. You know, how could we ever infer the full science of Edith Carina Nebula without having built this instrument? And remember, we're still at resolutions of tens of billions of kilometers here. We're nowhere near down to individual worlds to be able to see those at that distance. The last thing I kind of wanted to show you here is, for the moment, is just actually the Vista. This is an infrared image of the center of the Milky Way galaxy. It's a 1 gigapixel image. If you wear this, it's online. You can zoom in. I hope I can zoom in. And as you zoom in, whoops, you begin to see more and more stars. But you keep zooming in, and it just keeps resolving to more and more stars. Whoops. And it just goes on forever. I'll zoom in further. The image is 80 million stars. We say the Milky Way has what? So one of 400 billion. So let's say it's 100 million. That's 100. It's 1,000 of the stars in the Milky Way. How can we possibly ever hope to analyze something like that? I'm trying to zoom across. It just goes on forever. Every one of those is separated from every other one by the same separation of the stars in our sky. Bit closer. And every one of them likely has trillions of worlds around it. That's the scale we're trying to understand. That's the task. So individual telescopes on individual worlds will get us, and we have to continue that route because that gives us the specific information. But to understand the dynamism of any system, from a solar system with 2 trillion worlds to a galaxy with 2 trillion planets, we've got to think about it on a different scale. And that's where we're at now. That's where we've been at actually for around 10 or 15 years. But the computing power and the instruments haven't been there to kind of tackle that, but now they are. We're getting there. So just to summarize all of that, we're looking at the universe in terms of, I've put a bit more detail into this talk that maybe we'll go through because actually I might use it somewhere else. Actually, and to TU Dublin, which I'm a member of, they have a new lovely series for non-science students to do Horizon Series talks, and I thought maybe I might propose this. It seems you asked me, so there's a bit more detail in the next slide, but we'll go through it. But I suppose in a sense we can divide down the big questions into the universe. Is it, and the big questions there are, I'll step forward a slide actually. With the modern theory on the universe is what's called the lambda cold matter dark matter model. I got that wrong around. I'm like CMD model. Now the thing is that what I suppose I'm trying to say here is the ideas of an expanding universe and the ideas of dark matter and dark energy are not just arbitrary ideas. Like you kind of hear dark matter and dark energy. Oh, I don't really believe they exist. That's our modern theory. It's Einstein's theory of general relativity. And then imprinted upon that are these things called the Friedmann equations, which explain the expansion and the acceleration. And what this theory basically proposes is that the universe has gone through different eras of, in the early universe, normal matter dominated. Then with the galaxy formation, dark matter dominated to form galaxies. And now we're beginning to see a dark energy dominated universe that's expansion is increasing. And that's just the theory. We have the mathematics for that. It's in the Friedmann equations. But we need to test it. Science demands you test your hypotheses. And we haven't been able to test that, but we think now we can. We think now we can with vast new surveys. As in, as you see with like the LST Variable Telescope, by surveying 20 billion galaxies. That's where we're going with this. So with cosmology, and why is this important? It's important because, well, we need to know if our science is right. I mean, I always say this to people when they say, what's this esoteric science? Why do we need it? Quantum theory basically finished its mathematical formalism in 1937 with Dirac. And in 1946, we invented the transistor based on it. Took 9 years to turn the most esoteric quantum theory into a technology to define the rest of the 20th century. So it's not up to us to decide what's the relevance of knowing the correct cosmology. That's for future generations. It's up to us to lay down the best carpet we can for them to walk on and to move forward into a future technological development. And so the questions of our time And you talk to many theoretical physicists, they're frustrated because we can't build particle colliders big enough to test their ideas, but we may have other means to do it, as we'll see now in a few minutes. So I've kind of broken it down into with questions about cosmology, with questions about our Milky Way. We know broadly its structure, but how did it come about? What's the fine-grained detail? And then that links into then exoplanets. We're interested in, well, okay, we found 6,000 planets, but really, how many are there? What are they? What are their chemical structure? We are now figuring out how to detect them. That's still very biased towards hot Jupiters. We need to figure out ways that there are big planets close to the star that are easy to detect. How can we find Earth-sized planets further out? And then for all the planets we detect, how can we characterize them? That's the kind of question. And for our own system as well, to know the truth of the system, because if we understand the structure of our own solar system, it will help us to understand the structure of, if not all solar systems, at least for the generalized understanding of solar systems. So I've kind of preempted this slide a bit in that they're the great questions. Is our Friedman theory a model of the, that lambda CMD model of the universe right? And there's another side to this as well, because while general relativity might explain the grand structure and behavior of the universe, we know we got a problem in physics because quantum mechanics and relativity don't meet. There are problems. I mean, one of them you might know of is general relativity says the fast things that can happen at the speed of light. Quantum theory says entanglement happens much faster than the speed of light, if not instantaneously. They can't both be right. So we're looking for what we call a theory of quantum gravity. Now, we can't test that in lab. We're going to operate big enough. So where we can test quantum gravity, or at least the limits of general relativity, is to observe the behavior of gravitational objects, say like neutron stars, beside black holes. But the thing is, you need clocks, or you need observations that can monitor that at a trillionth of a second, a millionth of a second. How are you going to build a telescope big enough to observe a neutron star's rotation with the accuracy of a millionth of a second? That's the challenge. That's the square kilometer array, by the way. We'll come to that. So the thing is that even the cosmology is tackling the great questions of the cosmos, but also trying to grapple between this issue, the conflict we know there exists ultimately between general relativity and quantum theory. Again, what's the characteristic of our Milky Way? How did it evolve? How is it interacting with all these satellite galaxies we're discovering? How did the Earth come about? What are the number of stars? What are the number of planets? These are all wide open questions. We don't know if it's 1 or 400 million stars. Some people say there's 1 trillion planets, 2 trillion, so forth. Some people hypothesize up to 6 billion Earth-like planets, and possibly 100 billion Earth-sized planets. Sounds very optimistic to me. That's what they say. And then for all the exoplanets, how do we, as they get a full census of this, of all kinds of planets, and then characterize them, their compositions, their atmospheres, ultimately, why? Because we're asking about life in the universe, can we detect biosignatures? So they're the great challenges, and they're vast. And so the traditional way of approaching things will have to continue. We will need Keck, we will need VLT, we will need ELT, we will need James Webb and other new telescopes to do the fine detail analysis on the individual systems. But we've got to start asking these more grand questions about population, census, the grand scale number of things, the likelihood of life arising, the likelihood of number. Can we just get out of the kind of the hypotheses in this and start to actually tackle it from an experimental sample? And the answer is yes, we think we can. Through vast surveys and census of enormous populations, billions of entities. And by measuring them over multiple ways, their position, their precise motion in unprecedented precision ways. So again, I'm jumping forward to Gaia here, 1,000 times the accuracy of position in the sky than any ground-based telescope can achieve. Their brightness, so that we can infer their composition or maybe changes over time. Spectral analysis tells their composition. Radio information to understand the movement of billions of galaxies through dark matter, or as I say, pulsars near black holes. And then, we're now talking about monitoring activity, events in real time, not just observing things. So monitoring supernovae explosions, gravitational wave influences on spinning pulsars, literally planetary formation. I mean, again, I'm jumping ahead to what we're going to tell you a little bit more about in a few minutes, but with the square kilometre array, we're talking about monitoring in real time dust forming pebble-sized entities in protoplanetary distance around stars. and in real time observing organic synthesis occur in planetary societies, planetary protodiscs. So literally being able to observe real activity that we think is important to origins. And then to monitor hitherto unseen details and characteristics that we don't know yet. What we call discovery-based science. It is, again, I'm not the biggest expert in AI and machine learning. Actually, I've only been involved in one project in it. But up until now, we've hypothesized things as humans and then go explore it. Or actually, that's what it's supposed to be science about, isn't it? Here's my theory, now go test it. But you know, Isaac Asimov says, you're doing that and then something odd happens and you go, oh, that's odd. And that's the real science. Discovery is the thing you didn't intend to do. But in any case, the difference with discovery-based science is that we can now use our artificial intelligence. And I want to just step away from that. It's more machine learning. It's more actually data science we've had around for decades, statistical analysis, to be able to observe patterns in nature we weren't even looking for. And even now we might be able to get the computer models to be able to infer function or point towards new science theories. So again, there'll be an ethical question about this, is that, you know, or at least a human nature question is, we mightn't be involved in the science discovery anymore. So how do you feel about that? Discovery-based science is discovering the science from unsorted data that a machine is looking at. We mightn't have any involvement in it. So again, to get a bit more specific on this, I'll try and rush a little bit. So we're talking about monitoring billions of galaxies and therefore infer something about dark matter. Their movement and their distribution will tell us something about dark energy. Looking at millions of supernovae. In the Milky Way, again, looking at pulsar timings to extreme timings, looking at the position and motion of billions of stars, looking directly at protoplanetary disks. I should say, by the way, one of the most beautiful and elegant or eloquent, whatever word is, ideas is this. We can, with some of these surveys coming up, say the Square Kilometre Array, or even a subset of it, if we're observing millions of galaxies beyond the Milky Way, one of the things we can observe in their radio waves is what's called their polarization. So a wave's polarization is actually its orientation. If it's vertically polarized, it's going up and down like that. If it's horizontally polarized, it's going back and forth. But the Milky Way's magnetic field will alter the polarization of incoming radio waves. So by looking at the radio wave polarization of millions of galaxies, we'll actually do a dot-by-dot mapping of the Milky Way's magnetic field. Isn't that beautiful? But we need to look at billions of galaxies to do it. That's another thing that's Square Kilometre Array. And of course, we see the magnetic fields as so important, like the highway of charged particles, telling us about, again, the processes that are going on in the galaxy and maybe even the transfer of minute material from one star system to another. So with this new approach, we're talking about trillions of measurements, exabytes, which is millions of terabytes of data. And the data is unstructured, as in we'll just gather it, and we'll have so much data that we won't really store most of it. We'll use, again, our algorithms to analyze it and dump it in real time, because we just can't hoard that amount of data. We'll need new kinds of computing. So, for example, again, just preempting the tree. I'm going to talk about tree in a minute. Gaia, Square Kilometre Array, and the Vera Rubin telescope. But the Square Kilometre Array, they're talking with CERN. CERN are talking about going to what we call the high luminosity CERN. So they're talking about a whole new scale of what they call exascale computing that may revolutionize computing all over again. If there's only one reason why Ireland should be involved in Square Kilometre Array, is to get involved in the computing, let alone the astronomy. And then these whole new ideas, which are there anyway, because they're coming with cloud computing and the demands of the web, scalable computing, virtual resources, cloud computing, elastic computing, which is kind of the resources on demand when you need them. So you don't actually hog the resources if you don't need them. And then we have the analytical techniques in place. We don't even need, well, in fact, maybe you don't even want to go to large language models. You actually want earnest machine learning algorithms. I've just kind of given a list of them here. This is with a nod towards the talk in Tala and in TU Dublin. So we have, I suppose what I'm trying to say is, we have incredibly well-defined algorithms for finding classifications of objects. Regression is just graphs. Have we got a trend? What can be predicted, from a trend? Can we extrapolate? Clustering algorithms, anomaly detection algorithms, time series monitoring, or their brightnesses over time. All of these have been done manually by individuals on individual stars or individual galaxies over the decades. But now we've grouped them together in libraries of functions for Python and for R that just can be run on vast scales and vast cloud computers and basically do all the analysis you want on this data that you gather. So there's no magic behind it. There's no mystery, and there isn't even, as I said, it's why I could give this talk in 2017 as much as now. There isn't. It doesn't require agentic AI or anything like that. However, on reading some of the websites, you can now see that the likes of Sarah and Square Kilometre are talking about using AI to manage all of this. So it's coming in whether we like it or not. But the big data kind of sphere is well tried and tested algorithms that we know work. And then, of course, that's got to be organized globally. So over the last 10 years of SPAN, for example, the IAA, the International Astrostatistics Association, ADASS, that's a conference that happens every year, the Astronomical Data Analysis Software and Systems, but also each individual group. So Gaia have 9 data centers around Europe, and it's a big consortium. They've been actually developing since about the year 2000. So many of these projects have been running for decades with mindful that we're going this way. But they weren't ready in 2000. They weren't ready in 2005. Like the Large Synoptic Telescope or Vera Rubin Observatory has been developed for the last 25 years. It just saw first light last year. Plenty of online tools, and then the projects. Then I mentioned the Gaia, LSST, the Square Kilometre Array, and not just those, but even if you look at, for example, the new Chinese space telescope they're proposing, their images will be 300 times the area of a Hubble telescope. That's verging on big data at the same resolution. So these are telescopes. Their telescope can be used for huge survey work, almost like LST, which is 49 times the width of the moon, or the area of the moon, I should say. So let's just talk about a few of these projects. You may be aware of ESA's Gaia Space Telescope that it basically finished doing its observations about a year ago. It launched in 2013. It went out to actually one of the Lagrange points, the same Lagrange point as the James Webb Space Telescope, so a relatively stable orbit. And it's 2 mirrors, kind of rectangular shaped, over a meter wide, but with extraordinary capabilities to actually measure what's called astrometry, the position, the actual position of an object in the sky, and therefore, if you take multiple measurements of it and it moves, then to determine its motion. It also then has a spectrometer on board to analyze the light of objects to determine their composition. And then, of course, it's got an amazing CC detector, so it can do photometry, measure the brightness of things. So its objective was for a 5-year survey. I think it lasted longer than that. It has monitored with incredible accuracy 70 measurements at least of 1.7 billion stars. In fact, it's up near 2 billion stars in the Milky Way galaxy. Their position and therefore their motion with multiple measurements. Position using parallax, by the way. And I need to mention the distance ladder here. So an awful lot of Gaia is the brainchild of a British astronomer called Michael Perryman. In my view, one of the most unsung heroes in all of astronomy. He actually came up with the Hipparchus mission, which is the first mission in the 80s to monitor 137,000 stars. And he was able to measure a direct parallax, that's using trigonometry, to find the direct distance of stars out to about 130 or 300 light years. Gaia originated from Michael Perryman, and he's been given very little credit. I actually wrote to the Royal Astronomical Society about it. I told him it's like as if he's being ignored in the UK. He should have all sorts of awards. It's a bit of a disgrace, frankly. I don't understand it. I don't know whether or not just they don't get it, or maybe because he worked for ESA and wasn't on British soil that they're saying he's not. I don't know what it is, but he is the brainchild behind this, and he knows Lorraine Hanlon very well. He even gave a summer school here, actually in this building. I attended it for a week. An absolutely amazing speaker, but a brilliant mind. And his whole idea was if you can measure the distance of stars with precision, then you can analyze then everything else about them. Their size, their mass, their composition, and therefore the evolutionary processes going inside them. The distance ladder. And Gaia is giving us direct parallax measurements of 2 billion stars out to 30,000 light years. So it's gathered all the data. It's going to release a new version of the catalog later this year, release 4. But this is mind-blowing. It's got extraordinary computers, like 9 major computer centers analyzing the data right now, and the catalog in full won't be released until 2030. They actually had was it 440 mathematicians and general relativists working on the analytical maths behind it for, I think, something like 2 decades. So the long and short will be that will come out of this is just a ton of extraordinary measurements of 2 billion stars, about 1% of the Milky Way. And that gives us then the ability to be able to infer so much around that. There are some results out. So for example, some of the things that they're hypothesizing it will do is give us the radial motion. That's the actual motion to or from the Earth for 150 million of those stars. Actually, also monitor 10 million of the galaxies and 500,000 quasars. Discover every Jupiter-sized planet out to 160 light years. Astrometric. That is by the wobble of the star. Every planet around every M-type star, red dwarf, out to 320 light years. The interaction of every star within 160 light years of the Earth cloud over geological time, even possibly which star caused the dinosaurs to die. And the discovery, along the statistics are mad and getting bigger every year, 300,000 new asteroids, Kuiper Belt objects and near Earth objects as well, and on and on. 3 trillion measurements, 50 gigabytes of data per day. I was involved in one space probe, Integral, and we had a 64K link. They're getting 50 gigabytes a day. 9 consortiums around Europe. And UCD has a lovely connection through Professor Lorraine Hanlon. She developed a tool. She got an award, I think, about 800 grand about a decade ago to develop GAVIP, which is basically these data sets are so big, you can't download the data. You upload your code to where the data is. And she wrote an interface, or her team in this building wrote in a company called Parameter Space. I think they've evolved now to do earth science, but basically they developed one of the tools to actually interface with the Gaia data set. So the calendar that's going to be released, actually, that's wrong. It's the DR4 will be released later this year. So they've got now the exact position and brightness of 2.7 billion objects, the radial motion of 650 million stars, more than they said. They've actually characterized 800,000 variable stars and binary star systems. And dust, we'll see this now in a minute. They've actually looked at the dust interference of 87 million stars to map the dust of the Milky Way, precise orbits of 150,000 asteroids, and they anticipate they'll release actually a catalog of 7,000 exoplanets. Now, we've only detected 6,000 a day otherwise. And it's time to look at some images. So this is the best kind of, as I say, human-viewed image of the Milky Way. Here's Gaia. That's its map of the Milky Way, of the position of 1.6 billion stars. Remember, Gaia isn't just looking at stars in the locale, it's looking at stars all over the Milky Way. So this is literally a map of the shape of our Milky Way, as if we were seeing it from above. Just to print on it down where we are. We're in the Orion Spur, and there's just some of the spiral arms. Some of the other discoveries, well, actually, beyond what we normally see at night, it's a warped disk. And we know why that is as well. So again, so these are just some early results from Gaia. We also now know that actually there was on the disk there's 2 disks, a thick disk and a thin disk, and the thick disk comes from older stars from a collision with a very large dwarf galaxy 10 billion years ago. There's the it's very like what we would photograph, but the dust here, every point on this, it looks like a haze, is a star, and the dust is where it monitors the dust being blocked by. Or the star being blocked by dust in the foreground. We now know there are 90 satellite galaxies around the Milky Way. 90. We knew of 50. It's found 40 more, and it's currently going through a number of interactions with a dwarf galaxy called the Sagittarius dwarf galaxy, which may have caused. This is a video that has a bit of a mind of its own. May have caused the formation of the sun. So I get it running there eventually, but for the moment, I'm not sure why it took one. Here we go. So, keep running. That was 6 billion years ago. Star jump, just where we were, and this is what it's doing at the moment. So that was 2 billion years ago, collided again, and then about 1 billion years ago, collided again, and this is where it is now, and we've inferred this from the movement of the stars. There's no way we could infer this from just images. We have to see the movement. Okay? Sorry, I've lost the image. So, also what's happened is we also can see that every time it hits our galaxy, it like dropping two stones into a pond and they ripple and touch each other. So whenever it would hit, it would cause ripples in our galaxy, which we see now, one nearby called the Radcliffe wave. It's 9,000 kilometers long. 9,000 light years long, 400 or 500 light years high and wide, triggering star formation. which has had an influence on the Earth in recent history. So it triggered about 14 supernova around this bubble, including the Pleiades, or may have triggered, which then caused the expansion of the local bubble of which we're in. And we can even plot our course through this bubble. We think we came from the Orion Eridanus bubble, which is in the direction of the constellation of Orion, 18 million years ago. And we entered this bubble caused by the Radcliffe wave 5 million years ago. We're in a very calm, stable part of the Milky Way right now. So this is the kind of dynamics we can see from Gaia's data just by monitoring the movement of stars. Why do we think we collided with a big dwarf galaxy 10 million years ago? 10 million years ago, because they monitored about 30,000 stars in a coherent path that just have nothing to do with our Milky Way, and they run the time back, suggest it was a large dwarf galaxy 10 billion years ago we collided with. So that's just some results from Gaia so far. I need to move swiftly on. You can see a few yawns. We're probably getting tired. The Square Kilometre Array. Now this is such a crazy project that it's taken much longer to get going than had hoped. I went to a talk. Do any of you remember a conference in 2011 in Dublin called ESOP, the European Science Open Forum? I actually was made go to it by my boss. It was in July, and you had to drag me out of the place 4 days later. It was absolutely mind-blowing. I'll tell you, one of the most amazing sessions was by the AAAS in the States. They run the Science Journal. And they were like guys out of film noir, these American guys. They've been through it all. They sat in a small room and gave you the keys to the mint on how to get science funding. I left that room thinking, oh my God. And I went back to my college and applied for funding, got 44 grand that autumn. I just followed their recipe of how to write a proposal. It was unbelievable. But anyway, one of the things is they gave a talk on the Square Kilometre Array there. And back then in 2011, they had hoped that actually phase one would be done by 2023. It'll finish, it's undergo. It's about 130,000 low frequency antennae, like iLOFAR that Peter Gallagher put down in Burr. Now, LOFAR is European wide and it's 20,000 antennae. LOFAR Square Kilometre Array will be 130,000 across Australia and Africa, followed then by phase two, which would be 5,000 dishes, 12 meters wide. That would give it, I think, it's not a square kilometer. It's about 0.7 of a square kilometer. But the capabilities of this, if fully built, would be extraordinary. Back then, they actually asked Nokia, how long would it take to build the network interfaces for all these instruments? And Nokia said, if we doubled our manufacturing capacity, we could build the network interfaces in 2 years. And this will gather as much data as about the rest of the planet combined in all telecommunications. It's crazy. So it'll be 50 times the sensitivity of any radio telescope today. And the kind of the numbers behind it are just staggering. So they'll monitor early three-dimensional rippling in the universe just after it's born. They'll be able to map the detailed motion of hydrogen in 1 billion galaxies. That will allow them to map the dark matter for those galaxies. It'll be able to monitor as a pulsar spin rates to a picosecond. It will be able to observe dust to pebble formation in protoplanetary disks. Monitor, my alarm telling me about 10 minutes left. That's okay. We're doing okay. Directly monitor protoplanetary disk formation on a year-by-year basis. Observe organic synthesis. And make detailed mapping of the Milky Way's magnetic field. And SETI, by the way, as a sideline, times 1,000. Actually, the statistic that blew my mind was they could pick up a walkie-talkie at 14 light years. That's how. This is all about sensitivity. Area to gather very, 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 very weak radio waves. That's what will give you the clear signal to be able to monitor, for example, the radio emissions of a pulsar spinning at 1 million millionth of a second. That's how you test Einstein's theory of general relativity at the edge of nature. And this is what blows me away about these projects, is that science proposes the question at the very top of science, and somehow society will fund the project. And the one thing I love about astronomy, here's my little preachy bit here. Screw politics today. All of this, doesn't matter if it's China building it or America building it. What was Martin Luther King and Obama used to say, that the arc of history is long. Do we care about Khrushchev and JFK when they landed man on the moon? We only care about landing man on the moon. These projects, I wish there was more good news about them because they give us hope. We are literally mapping the future of humans' technological and scientific capability, or building it. And so we're still. I'll start to worry when we stop doing projects like this. If we're asking great questions in science and society is somehow willing to fund them, we're probably hanging in there, at least in a positive way. Again, just crazy off the scale. In fact, CERN and Square Kilometre Array are merging, I say, to form what we call exascale computing. They reckon they'll revolutionize computing all over again. They have to cope with the sheer amount of data. And to finish off, the Vera Rubin telescope, or the Large Synoptic Survey Telescope. Well, it's the Vera Rubin Observatory, actually, named after Vera Rubin, who was very much involved in the analysis of dark matter, or galaxy formation. But I think they're related, of course. But anyway, here's some of the statistics of this 8-meter telescope now coming online, first light last summer, to be observing 20 billion galaxies, 17 to 20 billion stars in the Milky Way to magnitude 27. Astrometry is 3 milliarc seconds, not quite Gaia, but actually, if you read in fine-grained detail, Gaia goes to 10 micro arc seconds. So that's 30 times better. So the thing is that basically, we're still getting amazing astrometry. So we're able to monitor the motion and movement of all these stars. But for many millions of those stars, we can tie in with Gaia if they mount to the same stars to get better precision. It's estimated that it'll discover 6 million solar system objects, including 5 million main belt asteroids, 100,000 near-Earth objects, possibly every near-Earth object down to 100 meters. Screw Elon Musk's idea to go to Mars. We don't need it. We've found the risk. We'll manage it. That's the risk. It'll generate 7 million alerts per night. Now, we typically generate a few hundred, maybe, around the world. Right? It's hoped to discover 1,000 extragalactic supernovae every single night. All of these have to be followed up. It's actually going to be a field day for top amateur astronomers to get involved in the verification process. It's absolutely mind-blowing. And I mean, it's monitoring, as I say, the brightness, position, and movement of 20 billion objects. It amounts to its imaging the southern hemisphere at near Hubble resolution every 3 days. That's what it's doing. And as a result of that, for 10 years of this, it will generate, well, let's talk about the link. The link from Chile to Florida, it can get up to, it's not always that, 50 terabits per second, 40 terabits per second. 15 terabytes per night, 500 petabytes, total 30 trillion measurements. And from all of this, then we'll be able to, basically the way I kind of view it is, it's going to use 20 billion galaxies as if they were buildings on the ocean to monitor the movement of the ocean. We're going to monitor the motion of the universe in real time and map the dark matter of the universe and map the shape of the universe, the actual geometry of the universe through the movement of, or the influence of dark energy. So it will feed directly into our fundamental questions. I'll show you, we'll finish off with 2 images. Actually, Gaia's image of Orion moving over the next 100,000 years, but also you've probably seen it online, the Vera Rubin first light image. So just this one image, it's 49 times the size of the moon, but in just that one image, they discovered 2,104 new asteroids, 7 near-Earth objects, 9 trans-Neptunian objects, and there are 10 million galaxies in this one image. Let's find the image. So web browser, put up here. Nope. Go on the Google browser, so picked up. Yeah, it's the other. Yeah. So this is the first. You can go online and zoom this. In fact, it's hard to find on a website. I don't understand it. You have to go and find a thing called Sky Viewer. So this was the first light image. It's just an example image. It's 49 times the area of the moon. The telescope has a 3 gigapixel. It's a 3 gigapixel camera with an 8-meter wide aperture. So that's what it really is. And if we just kind of zoom in on this, let's see if we can do it online. So let's hope it works. Yeah. So just keep zooming in. Oh, I've gone too far, of course. I want to actually go down here. Zoom. Yeah. Click it. Let's see. It's because it's actually going over Zoom as well, and you know it is not great.
Is the plus sign on
Is there a plus sign somewhere? Can you see it?
over to the right of it?
I'm not seeing it on my screen, actually. Yeah, I'm not seeing it. It's covered by this here. What's that there? Can I get rid of that? It's a zoom thing. Oh, there we go. Brilliant. Well done. Yeah. So you can see what happens when we just keep zooming in. We're getting more and more, again, Hubble-like detail. I'll just go into this little triplet of galaxies up here, which is most people's favorite. And everything in this image is a galaxy. Except for if you see the fraction of flights here, but almost 10 million galaxies. This is just 3 hours observation. Just doesn't pixelize. And that's not pixelization there, that's stars, you know? So, and you can just zoom around these images. They're not delivering these images very often, actually, unfortunately, not delivering loads of pretty pictures, but it's just a kind of a demonstration of the capability of the camera. And again, look at where, if I just zoom back out where that was. The whole image, you can zoom in all parts of it and find that. And people found over 2,000 new asteroids in the main asteroid belt that weren't known from that one image. And to finish off, I'll just go back to my PowerPoint and just show you then really a beautiful image of Gaia monitoring motion. So I didn't go through such. So here we go. So this is now don't pick just the bright stars. Watch some of the faint stars in the background. Everything is moving. So we got Orion's belt, Betelgeuse, Rigel, Aldebaran, the Hyades. It's hard to see it, but everything is moving.
Jesus.
What's the time scale?
Sorry?
What's the time scale?
Over the next 100,000 years for the whole movie.
Oh.
Now, it's much smoother when you watch it yourself on YouTube or something like that. In fact, there are very smooth movements of these stars on my screen. So they're being pixelated by Zoom itself.
And are we moving towards it or away from it?
Well, I mean, like, I'm sure we're moving towards some of them and away from others.
Yeah.
There's no reference. There's the Hyades, the Hades, whatever you pronounce it. That's what observing an object with extreme astrometric precision multiple times gives you. The ability to be able to predict the path of something. So, in just conclusion, oops, I want to just go back and look at my phone. So, these will provide deep insight into what it means, the terms dark matter and dark energy. They will reveal new details of the origin, nature, and evolution of galaxies, detect millions of planets of every kind, provide deep insight into our own solar system, comprehensively survey the solar system, and provide new insights we currently can't imagine. And there are a couple of cautionary things for me, because I'm big into the philosophy of science, is that, you know, this is a new era in science where we are kind of being put one step to the side. It will ultimately be, as I say, AI algorithms deciding on which, as I say, you know, data analytic algorithms to run, finding the patterns, inferring function. Now, inferring function means providing a mathematical description of what's going on there. That might be a science law. But the thing is that with science, we have things like peer review, ethics, you know. I know ethics mightn't come into astronomy right now, but it's still a new dawn, a new era for science that's just not runnable by humans. It's too big. And I suppose we just need to feel we have oversight on that as we move forward. Thanks very much.
Oh.